Having designed a new 30-pound combat robot in the last video, it's time to actually make the thing in preparation for the upcoming event in New Zealand. Obliterator is the most violent machine I've yet conceived and requires robust hardware to match. Most of the work will be spread between the CNC milling machine and manual lathe where appropriate. The week starts with large drivetrain gears, milled from off-the-shelf blanks that are held in a jig. This makes it easy to swap out gears without resetting the part location in software, and will be kept for future use. C45 steel is easy to machine, with the operation running smoothly. Finished with threads to mount the wheels, and now fit for purpose on the robot. A total of 4 gears are milled to have spares in case the first 2 are damaged in combat. Next are a set of aluminium caps for the weapon shaft, unassuming parts, but represent a bit of a milestone as these are the first pieces I've cut using tool offsets. Historically, I've had to set the 0 position of each tool every time they are changed due to only having one tool holder on hand. After purchasing more, each tool can have its length relative to the machine spindle stored in the mill computer. Therefore, after the top of the work is found with any tool, the machine simply adjusts its cutting height for secondary tools based on the difference in length. While far from a new technique, it's more efficient and repeatable than my previous methods and will be carried out in the future. Now the big ticket item of this entire build are the drive blocks, a pair of identical billet aluminium parts that more or less fixture the entire robot frame, support the drive motor and wheel, mount the side armor, and are a critical aesthetic piece. The part must start as a rather precise block of stock before 2 major setups are performed to remove the material from each side and form features. Afterwards, holes are drilled in a 3rd operation, finished in the drill press, then everything is manually tapped with threads to enable the support of the appropriate fasteners.
So the problem with having a simple robot with a small number of complicated parts when you actually have to sit down and make the complicated parts, this is probably the only one that will give any trouble. The rest are pretty easy. I had a go at it yesterday, messed up the origin, so this is a waste. I can't use it anymore, unfortunately. I've got 2 more blocks, which is enough for the robot, so they need to be faced. Run the code, it should just go. I've got Hudson in the shop with me today. It'll take the whole day to get these done, but then the rest of the robot should be pretty smooth sailing, so hopefully these go well, and then get the robot running soon enough. With the 2 blocks done, this top face isn't quite perpendicular, so it's marked. It'll be the one that isn't referenced from. And on the sides there's a little bit of a taper, so I've marked across this line it's equal to tapers in this direction. But this block is absolutely perfect in dimension and perpendicularity to the best that I can measure. So very happy with that. And I'm going to use it last, so if I do screw something up, I have a perfect block for take 3. But that won't happen because everything will go smoothly. So after, that'll be 3 days of work, or even perhaps a little bit more, we've got some completed parts. This is, again, by far the most complicated part in the robot, and possibly the most involved single piece I've ever machined on the mill. So yeah, we've got the 3 attempts here. The first one, screw up with the origin in the wrong place in the cam. The next 2 went very smoothly, and I'm quite happy with how they turned out. Because after the first one was nailed, the program is the same. As long as you set it up the same way, you'll just produce the next part. So I could more or less leave it as it was for today. Playing with tool offsets is again something I haven't really used before effectively. Every tool for this part was set in offset, so I just swap it and click go. One massive program for each setup, versus in the past every tool was an independent program because I had to reset everything between setups. So I'm really happy with these. The surface finish can be improved. Perhaps that's a tooling thing. The threaded holes were not tapped especially straight. I did those by hand. I don't really have a way to rigidly tap, which is when you put a tapping tool into a drill press or a mill. Yeah, I don't really have the ability to do that here with these 2 machines. So coming up with some sort of jig to ensure that the tap is held straight is a really good idea. That's probably the only blemish to these parts, at least that I've found so far. Just gotta, smash out the rest of the robot, which is going to take longer than I think, as it always does, but gotta get on with it.
Parts for this robot have been provided by PCBWay. They machined the weapon hub, pulley and aluminium frame plates, all of which were anodized to suit the theme of the machine. Bearing bores were made to tolerance, roller bearing races pressed into place without any trouble. The 4J pulley profile also fit the belt very well based solely on the dimensions provided in the drawing. Looking ahead, there were no manufacturing errors and each piece simply fell into place as intended in the CAD model. The parts are fit for purpose and should serve this machine well. With the drive blocks out of the way, some smaller parts can be quickly knocked out. First is the Hardock 600 weapon support, and it has its profile cut with a plasma cutter from sheet stock. One can usually truss this to within 1mm either side of the intended contour. In order to inset flathead screws, the 8mm holes need the appropriate countersink, which is easier said than done in hardened steel. The first idea was to use carbide-tipped wood router tools, which did 1 pass before chipping on the hardened hole created by the plasma cutting process. Rather than expend a $20 tool on each of the 6 holes, I recalled that I possess a CNC mill. Each hole is indicated with a probe, before a carbide end mill interpolates the countersink 1/4 mm at a time. The stepped surface is somewhat cleaned up with a router tool for a complete part. Next are carbon fibre plates to adorn the frame, milled out of sheet uneventfully, though they always require a lot of manual cleanup. Following are the plastic side armours that must be profile cut from another 2D sheet before being bent into shape. Plastic disappears rather quickly on any mill. Before long we have a pair of blanks. Small slots are cut on the underside to encourage a bend. The part is warmed with a heat gun before being reefed into shape, accommodating for a large amount of springback, sometimes more than 30 degrees. Over time the parts have settled even further, so it's worth keeping that in mind. Drive motor shafts are trimmed with a Dremel to not run against the drive wheel when it all ends up being assembled. These wheels are cast polyurethane on a 95A hub. Interestingly, the 45 and 65 Shore resins react very differently to the dye. 65 Shore was slightly transparent and maintained the green colour. whereas the 45 was opaque and skewed the green to a light lime. They are otherwise the exact same brand and product, so it's a bit baffling that there is such a stark difference. All parts are ready to assemble the two drive pods. The rubber wubs are softer than I remember, though there shouldn't be a problem in combat as long as they don't delaminate from the metal threads. First assembly is always done without Loctite or grease, just to ensure it all works, and later this will be pulled apart to ready it for combat. All looks in order, so attention turns to the weapon stacker.
Now this shaft material is really good. It's got an induction hardened case around the actual shaft bit, which means it's extremely strong, extremely durable, and the middle of it is still soft so you can drill and tap threads. But because of that outer core, you can't really touch it in a lathe directly. You need to grind it to mostly length and then just finish it with the heat affected area, because it's just too hard. It's harder than probably, I don't know if it's harder than the carbide, but it'd be pretty close. And I don't need to ruin any more tools today, so that's what we're going to do. Now, putting the weapon stack together for the first time, you got all the usual, caps and bearings and hubs and whatnot. But there's this space in the middle that doesn't look like a lot. It's arguably the highest tolerance, most important part, because between the two needle roller bearings, it's what actually sets the distance between them. It'll sit on that inner race there, just like that. I need to take a little bit off the diameter. It looks a bit too big. Regardless, the depth of it matters heaps, because as everything's clamped together, that's what will ensure that the bearings have the correct preload. If it's too big, it'll be loose. If it's too small, you'll just be binding up the bearings. So that's what I'm working on now, getting that right. So I'm not sure exactly where in the video this will be placed, but at this moment I've machined every part needed for the robot, and I'm redoing the spacer that sets the bearing preload. Originally just did it in the 3-jaw chuck, but then, as you probably just saw, I made a mandrel to ensure that those two outer faces are extremely parallel. Besides from these aluminium blocks for the drive, this would be second in line for the most effort of any part. It took 2 goes to get the mandrel right, it took 4 goes to get the spacer right and get the preload set correctly. But I think it was worth it. I don't know if it's going to carry across on camera. When I was originally spinning it on the A spacer, which is this, and the B spacer, the mandrel spacers in here now, you know, there's the tiniest little bit of maybe a high spot, but I swear now that there's none of that. It runs extremely smooth. Give it a poke. I don't think there's any high spot. It just turns, which is great. I think this is going to work, which means that we can go ahead and assemble the robot, wire the robot, and hopefully test it soon enough.
With most parts made, a dry assembly of the drive pods and weapon stack-up is performed. This is to ensure that there are no major faults with the frame plates or drive blocks, in case the weapon shaft pulls the holes out of alignment or some similar issue. All goes well and we have our first look at the finished machine. The 3D printer has been running almost constantly, producing the TPU parts to fit inside the machine, leaving only the rear frame block as the last part to make.
Something I've had to deal with a recent part is this rear panel for the robot. It's meant to be 55mm tall, but I've actually knocked it down to 49 and used a pair of 3mm plates to space it out to the actual width of the robot. And the reason for that is aluminium, you can get in all shapes and sizes, but I like to buy it in flat bar form, and robots like Derive, which was my first feather, the entire thing was exclusively designed around frame pieces made from these generic sizes, right? And it was specifically made, let me just make sure it's the right one. Yeah, this stuff. This is 16 by 80 flat bar, this in really long, I think up to 4 meter lengths. And it's very economical to buy in large quantities, and it's easy to cut up and put on the CNC machine. So for 20mm stock, you can get it in 20 by 50, but any bigger than that, and you go outside the sort of normal flat bar range that I've accessed at the local store, and I got here 8 by I think 160, and there's 10 by 140 and 12 by 120, and all sorts of sizes in between. And that drives a lot of my designs as these standard sizes, and it'd be really good, even, you know, if you don't have a CNC mill, fair enough, you can still make a very competitive and strong frame out of these standard sizes. Just cut it, you know, with an angle grinder or what have you, and just manually drill the holes and pocket it out, and you'd have something that's very similar in strength to, you know, the best CNC machined part I can make. It's the same stock. Of this 20 by 50, I've got 4 meters of it for 150 Australian dollars. And that one, like, you know, length could be by far your entire feather chassis with spares. So I think it's a really good way to get 6061 alloy in economical sizes, and I'm going to continue to use it. At the caveat of occasionally you have to do weird stuff like this, but, you know, so be it.
Leading into wiring, the robot is mechanically assembled for the first time without any issues. Wiring also went pretty much without a hitch, assisted by my grandfather Dave. First tests will be done with a VESC speed controller. After first power on, each drive and weapon ESC needed to be programmed to correctly spin the motors. This machine was originally intended to run Turnigy batteries from Hobby King, but annoyingly, both the original and RMA pairs delivered to me were dead out of the box, with cells ranging from 1.5 to 2.6 volts. I'd expect this robot to use all the capacity and current these packs can provide, so running a damaged one is not acceptable. New batteries are on the way from a different vendor, and I won't be purchasing batteries from them in the future. After all that work, the robot was ready for a spin test. Running a conservative VESC tune, the machine is clamped securely to sawhorses to prevent the gyroscopic forces from moving it should something go wrong. Humans were securely hidden away, and the weapon spun up for the first time.
you're coming.
Yeah, my goodness, that sounded awesome.
With a working weapon, the machine also drove quite well. It took a few attempts to get a better spin-up out of the Vesk. The best result was just over 3 seconds. It was worth testing the more simple red brick ESC next. From my understanding, this should give a much faster spin up at the cost of having no protections against catching a light if something goes wrong. Definitely an improvement, sitting at a bit over 2 seconds at full tilt. I cannot push the ESC that hard too many times in a fight though, as just 5 hard spins got it warm enough to be felt through the chassis. So that's where the robot is sitting currently. Apart from some minor wiring fixes, mounts for forks on the rear, and the correct paint on the weapon bar, it appears ready for combat in a month's time. Those tasks are on hold while the multi-brain is constructed, having only welded the frame so far. Ideally, that should be covered before my trip away. Until next time.